Alright, I want to make this video to help with force diagrams, which is what we see in 6.1 or 6.01, that lesson. Alright, so first of all, just the basics of force diagrams. When you draw a force diagram, you don't draw the object. You don't draw anything around the object. You're not drawing a picture. You can either use a dot or a box to represent the object. Okay, so even if it's a person, we're just going to simplify it by treating them like a box. Okay, if it's an egg, if it's a bird, it can be a box, or it can be a dot, just whichever one you like better. Okay, that's how we're always going to start force diagrams. All right, then the forces that act on these objects are going to come out from the object. Now, that doesn't mean that the force is actually coming from inside the object, but that's the way we draw them. All arrows must point away from the object. For example, if there is a force on this object and it's pushing it to the right, I would never draw an arrow like that in my force diagram. The arrow would always come out from the object. So the force is to the right. If there were a force to the left, same thing. I wouldn't draw it coming in. I would draw it going out. Alright? There's a couple of different forces that you should be familiar with. One force that is present on Earth 100% of the time is the force of gravity. So whenever you're drawing the force diagram for something on Earth, you will always have a down arrow. And you can label that down arrow FG for the force of gravity. Right. Now, beyond that, your forces are going to differ. If the object is sitting on something, like it's sitting on the ground, it's sitting on a desk, it's sitting on a hill, there will be a force called a normal force, and that force is going to be perpendicular to the surface. So as long as the surface is flat, like a desk or something like that, then normal force is going to shoot straight up. And you can call that Fn for normal force. Okay, if we're using a box, it would look like this. Now, if the object is floating in the sky, hanging from a shoulder, if it's not sitting on a surface, it does not have a normal force. So like if you're carrying a bag on your shoulder, there's no normal force working on that bag, okay, because it's not sitting on a surface. So normal force comes from something sitting on a surface, excuse me. Right? Another type of force that you could have that would be an upward force is the force of tension. You can call that Ft. That is caused by like a strap or a rope or something like that. So if something's hanging, then it could have a tension force up. Okay? Now you could also have a tension force, excuse me, not that way. Like if you have an object being pulled by a rope, then you could have a tension force with the object being pulled by the rope, or the rope could pull it in the other direction. Okay, and you could have a tension force. Another force that you could have is a force applied. So let's say someone pushes the object to the left. That would be a force applied. Or someone pushes the object to the right. That would be a force applied. You can have friction. Friction is always opposite to an applied force. So if the force is to the left, then the friction force, FF, would be to the right. Or if someone's pushing something to the right, then the friction force would be to the left. Now, there's no friction force if something is in the air, right? Friction is caused by a surface. You can have air resistance, which is a form of friction, but we only see friction like we're talking about right here if something is moving on a surface, on a desk, on the ground, okay? All right, now let's say something is falling through the air. So you have gravity pulling it down, but you might have air resistance. Okay, you can call that FR, force of resistance, going up. Okay, so that would be an example of something falling to the ground. So you get an idea here that we have different kinds of forces. We got our normal force on the surface. We got our gravity force. We got our tension force if we have like a strap or something, or a rope pulling something. We have our force applied, that's like a push or a pull, and then we have friction, which would oppose that force. All right, so let's look at some of the example problems in 601. Sarah's book is at rest on her table. So we got Sarah's book. We can do a dot for Sarah's book, or we can do a square for Sarah's book. Okay, you're not going to do both, but you can do either one. So what forces are at work at Sarah's book at rest on her desk? Well, Sarah's book is on the earth, so there's going to be some gravity. Either way you want to draw it. Right? And then if gravity is pulling Sarah's book down, what is pushing Sarah's book up to balance that out? Because remember, if the force is unbalanced, the book is moving, but the book isn't moving, so the forces must be balanced. So there must be a force up to balance the force down. Now in this case, the force up is going to be the normal force, because Sarah's book is sitting on a desk. Be careful because you want these two to be equal since it is at rest. Okay? If it was falling to the ground, you might want this one to be bigger because the downward force. All right? The trapeze artist who is sitting on the bar is suspended motionless from the ceiling by 2 ropes. Okay, so trapeze artist or trapeze artist, however you want to show it, gravity pulling her down. Alright, and then she's got 2 forces up. So we've got 2 ropes pulling her up, 2 forces up, and those are both tension forces. Now these two together should equal this one down because she is sitting motionless. So the up has to equal the down. So we could show the total up or we could show the 2 up, but they are tension. They are not normal forces. Okay? Those are ropes holding her up. I guess you could think of it as a normal force from the bar since she is sitting on the bar. So if you thought of it that way, if you're thinking of her sitting on the bar and the bar holding her up, then you could think of it as a normal force, but then you have the ropes holding the bar. So I guess it just really depends on how you're thinking of that. I didn't think of it that way at first. So you have those forces. Okay, so you can show the total 2 ropes must be equal to the down, or 2 ropes must be equal to the down. All right, an egg, so again dot or box for the egg, is knocked out of its nest and it's free fall toward the ground. So gravity pulling it down. There's no mention of air resistance here, so I'm not going to label the air resistance. After it starts falling to the ground, there's no force to the left or right. Now there was a force that knocked it out of the nest, but that force is not still acting on it. Okay, once that force acted, then it's over. All right, Catherine pushes her science book. So we have Catherine's science book. She is moving it across her desk at a constant velocity. All right, so we know that there's gravity, just like in problem 1. And we know that there's a normal force from the desk, just like in problem 1. But now she's pushing, so we can call this force applied or force push, however you want to think about it. You can also think, sorry, I ran off the screen. You can also think about her pushing it to the left, if that's the way you want to think about it, because it doesn't say which direction. The key here, though, is that it's a constant velocity, which means the acceleration is 0. The object is moving, but it's not getting faster or slower. So if the acceleration is 0, then all the forces must be balanced. So what is going to balance out you pushing your book? Friction. And it has to be equal in this scenario. Now there's a scenario later where they don't have to be equal, but it has to be equal here because it says that it is constant velocity. All right, so this is what would the force diagram look like here. All right, so that's 1 through 4. You have the rest that you could try again on your own and turn that in. You can resubmit if you've already done so. And I hope that that helps just a little bit. So thanks for your time.